Professor Dr. Snidley here. The captain is on holiday and doesn't wish to be disturbed until the first RaySpheres have been produced. This means more work for me, but also more fame. We will start implementing the vector type, which seems quite easy to do. It just supports a few functions, which means all the functions we will need for later RaySphere scanning. To make it a little more interesting, we shall implement the vector as a generic type. That way we shall be able to not only use doubles as the Ceepepporg version does, but also use floats. This could be interesting when performance is being optimized. Now that we have the very basics settled, being able to create such a vector, let's implement the add operation in order to be able to add two vectors together, generating a sum of these vectors. To do that, we will use the add trait, which turns out to be rather verbose. Lots of code to be written here, which is at least very explicit and clear, yet much more compared to the Ceepepporg version on the left side. It is absolutely worth noting that implementing the add trait in order to achieve a simple v1 plus v2 is trivial, but also involves copying the values around. This is why I was thinking, well, let's implement it for a reference type, right? If you do that though, then instead of saying v1 plus v2, you have to say address of v1 plus address of v2, because Rust aims to be very explicit about that. So it's either the one or the other. It's good to know though that you can implement all different combinations of reference types and value types for your trait accordingly, and then possibly make use of special optimizations. The next issue to tackle was the question of what kind of semantics I would want for the vector type. It seems like a primitive type, so instead of move semantics, copy semantics might be more what you would like to have. To do that, you derive from the copy trait. Copy semantics is what you would expect from a primitive type, which makes it more comfortable to use. On the other hand, this might lead to unwanted bitwise copies that are kind of out of your control or out of your scope of consciousness. Therefore, using ownership transfer might be a way to further optimize program runtimes. For now, I go with the copy semantics though, because I'd like to have it simple for a start, and later might go in and change that to use ownership semantics and see where that leads me to. Next in line are simple subtraction and multiplication operations, which are similarly implemented using traits. Now that we know how it works with add, it's rather straightforward to implement it for the other traits as well. You can just go by schema F. Just please note that currently we are copying vectors around quite a bit. So whenever an add is called, the source and left-hand or right-hand side will be copied into the function and a new vector is returned. As these are all marked as inline, we can only hope that the compiler will be able to optimize the heck out of this in order to prevent unnecessary copies. Now we will implement the first non-trait methods, which will be malf and malft. Malf will multiply each component of the vector with an arbitrary floating point number, whereas malft will do the same, but not alter the source vector. It's absolutely worth noting that whenever returning a mutable reference to yourself, you will need to work with lifetime specifiers. Lifetime specifiers will tell the compiler the exact lifetime of whatever you return. And by using the same lifetime specifier as you declared for your own self, you basically tell the compiler that whatever you return will live as long as you live, which makes sense because you basically just return yourself. Sometimes I do believe that the compiler might be able to figure this out by himself as well, because it seems so obvious, but you know, who am I to judge that? The next method to implement is without any doubt the most complex and mathematically taunting one. It's normalize, which does so much math inside that I can barely keep up. Certainly one of the greater things about floating point numbers is that they carry the float trait, which in turn allows to do common operations rather easily, like getting the square root of it. Something more difficult turned out to be getting one of type float. Many things are at play here. For example, t::1 does not actually refer to a function or method on a particular type. The only way you can access trait functions basically is by going through the trait itself. Therefore, t must support the float trait. From all I see here, t is constrained to support the float trait, but for some reason it doesn't really get through. So I'm trying, of course, to, instead of t::, I put float::, right? And the type of the actual float should be inferred. But yeah, well, that is just not the case. It is not happening. I don't know why, but I'm totally considering to be wrong, even though I am the well-beknown Dr. Snidley. It must have taken me hours, no, days, to finally realize that the issue I ran into was a known imperfection. Fortunately, there was a known workaround as well, which, once applied, made everything go just fine and as expected. Amazing. Also, I want to express my great gratitude towards the Rustacean engineering framework that allows me to post a question and get an answer within 15 minutes or less. It's quite incredible, but probably it's also my name, Dr. Snidley, which attracts lots of possible answers just because, it's the fame. What can I do? It is my greatest pleasure to announce that in the next phase we will most likely be able to synthesize our first Virtua RaySpheres. Virtua? Yes, I don't think we will produce an image just yet, but we will get very close to this. Maybe close enough to bring our captain out of his holiday. We shall see you next time.
That and more in our next episode of Trace Quest 5.